Right now, as you watch this, you are moving through space at roughly 370 kilometers per second. Earth, the Sun, our galaxy, all stacked into one cosmic ride you never signed up for. What if I told you there are places in the universe where 1 second for you could be hours for someone else, and objects so dense that a single teaspoon would weigh about 1 billion tons? Stay with me here, because by the end of this video you'll see why Brian Cox's favorite space facts aren't just cool, they're reality-breaking. Here's what messes with your head. The universe doesn't just have big numbers, it has numbers that behave like magic. Light, the fastest thing we know, moves at 299,792,458 meters per second, and yet gravity can bend it like a funhouse mirror. There are stars so crushed that atoms collapse into a neutron ocean, and we can literally hear them collide as gravitational waves, ripples in space-time itself. And on the largest scales, the observable universe is about 93 billion light-years across, even though it's about 13.8 billion years old. How can something be bigger than the distance light could travel since the beginning? If reality plays by rules like that, what else are we missing? Because on some of these questions, scientists aren't just curious, they're genuinely baffled. So let's build the normal story first, because this is where things get strange. We live in space-time, 3 dimensions of space woven together with time. Einstein's big idea is brutal and beautiful. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. That's why planets orbit and why light bends near a massive galaxy cluster, like the universe is running its own optical illusions. Now zoom out. In the early 1900s, astronomers realized most galaxies are moving away from us. Not because we're special, because space itself is expanding. Picture the surface of a balloon with dots drawn on it. Inflate the balloon and every dot sees every other dot receding. No center on the surface, just expansion. And here's a key twist. Expansion doesn't obey the speed limit the same way moving through space does, because it's space itself stretching. That's how the observable universe can be 93 billion light-years across, even though the universe is 13.8 billion years old. Light isn't cheating. Space-time is changing. So what should happen next? If gravity only pulls inward, expansion should slow down. If the universe has just enough matter, it might coast. But then the observations hit, and reality swerved. Because when scientists measured distant supernovae, exploding stars used as cosmic mile markers, they expected to find a universe gradually breaking under gravity. Instead, the data said the opposite. The universe is accelerating. And that's the moment modern cosmology quietly turns into a mystery story. Scientists gave the unknown a name, dark energy, which is basically the most polite phrase for, we have a measurement, not a mechanism. It's not an explanation. It's a label on the biggest question mark in the cosmos. Now, if you're thinking, okay, but we've got incredible instruments now, surely we can pin this down. You're right to think that. We've done things that would have sounded like fantasy a generation ago. We've detected gravitational waves, confirming that space-time itself can ripple and ring. We've even imaged the shadow of a black hole, seeing not the hole directly, but the silhouette of a region where space-time's point of no return dominates everything around it. So here's the cliffhanger. If we can hear black holes merge and see a black hole's shadow. Why is the biggest ingredient in the cosmos, this thing driving acceleration, still basically a ghost? Here's the main idea that could explain it. The vacuum isn't empty. In quantum physics, nothing is unstable. Fields jitter even at their lowest energy state. You can think of it like the universe's background hum, tiny fluctuations that never fully shut off. And one theory says dark energy is vacuum energy, the energy of space itself. Try this analogy. Imagine space-time is a stretched fabric. Matter makes dents, like a bowling ball on a trampoline. But vacuum energy is more like the fabric having a built-in tension, a pressure that's part of the fabric even if you remove every bowling ball. Empty space in this picture isn't passive. It has a kind of push. That sounds satisfying until the number shows up. When physicists estimate vacuum energy using straightforward quantum calculations, they get a value that doesn't just disagree with what the universe is doing, it disagrees by an absurd amount. This mismatch is often described as one of the worst prediction gaps in all of science. Not, we're off by a factor of 2. More like, we're off by a factor that makes you question your life choices. So cosmologists circle 3 big explanations like suspects in a case file. Option 1, vacuum energy is real, but something cancels almost all of it, leaving behind a tiny leftover that drives acceleration. Option 2, dark energy isn't constant. It changes over time, meaning the universe's push isn't the same today as it was billions of years ago. Option 3, gravity itself needs an upgrade on the largest scales. Our equations work beautifully locally, but maybe the cosmos plays by slightly different rules when you zoom out far enough. And this is where Brian Cox's favorite kind of fact hits. You are not a visitor to this universe. You are made of it. In the early universe, there was mostly hydrogen and helium. The carbon in your cells, the oxygen you breathe, the nitrogen in your DNA, the iron in your blood, those were forged inside stars and scattered through space by stellar death. You are literal star chemistry assembled by cosmic history. And that means the universe's expansion story isn't just abstract math. It controls whether galaxies form, whether stars ignite, how long they live, how many heavy elements get made, and whether complex chemistry ever gets enough time to become biology. So yes, dark energy affects all of us because it shapes the kind of universe where us is even possible. But just when you think you've got a clean narrative, the universe hits you with a second twist. Different ways of measuring the expansion rate don't perfectly agree. One method reads the early universe, patterns imprinted in the cosmic microwave background, the afterglow of the Big Bang. Another method measures the nearby universe, distances to stars, galaxies, and supernovae, building a cosmic distance ladder. And when you compare the numbers, you don't get a perfect match. You get an uncomfortable disagreement. Now, you might be thinking, so which one is wrong? And that's exactly why this is such a live mystery. It could be systematics, calibration issues, hidden biases, the boring but totally plausible explanation, or it could be the exciting explanation. New physics, dark energy could evolve. The early universe could have had an extra ingredient that changes how fast everything expands. Gravity could be slightly different across cosmic distances, or the vacuum could be stranger than we've dared to model. And remember that vacuum energy mismatch? If empty space is really that weird, it doesn't just affect expansion. It affects what nothingness means near black holes, in the newborn universe, in every corner of reality. The same question keeps coming back in different disguises. What is space-time actually made of, and why does it behave the way it does? So here's where we land. We have a universe that expands, and not only expands, it accelerates. We have a leading suspect in the form of vacuum energy, but the predicted amount is catastrophically wrong unless something cancels it. We have alternatives, changing dark energy, modified gravity, but each one opens new questions that could rewrite physics. And the best part is, this isn't a maybe someday story. This is happening in real time. With every new survey, every improved instrument, every better calibration, the possibilities shrink. We're not guessing in the dark. We're measuring our way toward the truth. So if you had to choose right now, which story do you believe? Is dark energy vacuum energy with a cancellation we don't understand? Is it a dynamic field changing as the universe ages? Or is gravity itself incomplete at the largest scales? Whatever the answer is, it's going to be one of those Brian Cox-style facts that doesn't just make you go, wow. It makes you realize you live inside a universe that's still keeping secrets. Secrets we're finally smart enough to chase. And this isn't the only mind-bender waiting. Because next, we're going into what black holes do to time, the strangest exoplanet atmospheres we've ever detected, and the most promising places to search for life in our own solar system. Thanks for watching. Remember, you're not separate from this story. You're made of the same physics doing all of it.